Okay, we were discussing about diode rectifiers, right? Specifically, we were talking about half-wave rectifier. Let us see a little bit more about the behavior of half-wave rectifiers and what are some of its limitations, right? So if you see the half-wave rectifier that we were discussing about looked something like this: a single phase half-wave, right? Single pulse rectifier. And then at the output you can have load, which we saw that, for instance, in a DC machine you can have probably some inductance, some resistance in a voltage source, right? Back EMF. So it could be ELR. This is diode, this is the input voltage V in. So if we redraw the waveforms for this particular circuit, then this is how the voltage waveform V in looks like, right? Let's say this is the back EMF E, right? And we defined alpha, which is the angle at which the diode would start conducting, right? And we saw that in this case, as the current starts from the point alpha, right, it would rise. It would have hit maximum value at this instant if there was no resistance, right? But because of resistance, it would hit a maximum value maybe somewhere before that, and then the current would start decreasing, right? And at some point the current would come back to 0. Now if you see in best case scenario, even if you do not have any resistance, right, even for 0 resistance, right, even for 0 value of resistance, you understand that because the area between V in minus E, right, integral over the time should be equal to 0. Therefore the area, which is the positive area, right, would compensate with the negative area, right, and it would become 0 before the end of cycle, right, and therefore the current would come to 0 before the end of cycle, even if you do not have a resistance and if you have a positive value of E. Only in the limiting case where R is equal to 0 and E is equal to 0, only in this limiting case you would operate the circuit in critical conduction mode, there wherein the starting current would be equal to the ending current of this cycle. So current will start from 0 and will end instantaneously, touch 0 at the end of the cycle, and then again rise. As long as you have R and E non-equal to 0, which would be the case if you are talking about an RLE load, then this current would be discontinuous. So that is one point. The other point, if you see, is that what about the energy? How is energy flowing, or how is power flowing in this case? So how is power flowing? When you see current I is the current which is flowing through the source, right? So whenever instantaneously, whenever V in into I, right, let's say we talk about let me just write here down that above circuit would operate in discontinuous conduction mode always for non-zero value of R and E, right, irrespective of the value of L that you choose, right? So this was one point. Now if you talk about the power, right, what is the instantaneous power? It is the input voltage multiplied by the current. So if you see from 0 to pi, right, between 0 to alpha, so theta between 0 to alpha, right, this instantaneous power, let me call it small p, is equal to 0, right? Between theta between alpha to pi, because the input voltage is positive and the current is also positive, value of power is greater than 0, which is good because the source is transferring power to the load. But then if you go from theta upwards of pi to beta, what is beta? Beta is the angle at which the current becomes equal to 0, or the diode stops conducting, right? Alpha is the angle when diode starts conducting, beta is the angle when diode stops conducting. So if you go from pi to beta, you see the current is positive, but the input voltage has become negative. So if you see the instantaneous power, it has become less than 0. Now this is something which is not really desirable, right? The negative value of P is not desirable. Now why do I say that it is not desirable? Because you see, your aim is to transfer power from source to load. Here you are taking power for most of the duration from alpha to pi, but then you are again pushing back part of the power, right? So if there is a series resistance, for example, here there would be losses in the diode and so on. So unnecessarily you are actually taking a little bit more power and then giving back a little bit of power. So a net power gets transferred to the load, but then some of this power gets wasted in this exchange, right? So it's not desirable to have power flowing back into the source if your agenda is to actually absorb power, right? If you see, that is practically when we talk about AC systems and linear AC systems, right, wherein you do not have diodes, which is a non-linear element, you have only voltage sources and resistance and inductors and so on. You would like your load to operate at unity power factor. What does unity power factor means? Unity power factor means that your voltage as well as current, right, both should be in phase. What does that mean? That if you multiply the instantaneous power, it would always be positive. The instantaneous power plot, if you plot instantaneous power, it would always be positive, right? And if you do not have unity power factor, then the instantaneous power becomes negative, which is not desirable, right? So essentially, we would not like power to flow back. So this was an example of a linear circuit. Ours is a non-linear circuit, obviously, right? But here also we would like to maintain that power should not flow back. So this is another, or rather this is, I would say, one of the limitation of this circuit, right? Now how do we take care of this problem? Let's see, before going ahead, let me tell you one more limitation, which is in a way related to the same thing. That thing is, if you write this expression, let's say as, let me call it as V1, right? So let's say this expression is V1. Now what is the waveform of V1? Let me try to draw in this same diagram. So the waveform of V1 is, it's E, since nothing is conducting, right? Then it follows this waveform and it continues to follow this waveform till it stops conducting, and then again it becomes E, right? This is instant beta, this is instant alpha, right? So essentially this is the waveform of, sorry, I've drawn it a little bit extended. After this another cycle would start. Yeah, so this is the waveform of V1. Now if you see V1 has a positive component, but V1 also has a negative part of it, right? V1 also has a negative part of it. Now what will that do? It will increase the ripple in the current that is flowing in the load. Why? Because if you only, so ideally what would you want? Ideally you want V1 to be, if V1 would have been flat constant DC, right, you would have absolutely no ripple in the output current I, right? You see this loop, there's V1 that you are applying, right, and there is L, there's R, and there is E, right? So if you see in this loop, ideally you would, if your V1 would have been pure DC, then you would have absolutely no ripple, and this current would be ripple free. But now, because you have positive voltage and sometimes you have negative voltage, so what will happen when your voltage is greater than E, your current would rise, and then when voltage is negative, current would fall. So more the ripple in voltage, more would be the ripple in current. which is again not desirable, right? So higher the ripple in voltage, higher is going to be the ripple in current, and which is also not desirable. So how do we sort of solve this problem? If you see, there are three things, but in nutshell, let me say these two things is the major thing. One is the power flowing back, which is not desirable, and other is the large magnitude of voltage ripple. So the circuit that we are going to see is actually a half wave, but it also has a freewheeling diode included to it, and that is what helps us solve this problem. Let's see that circuit now. So I would also, you can say, just to remember it, it's a DD-RLE circuit, which essentially implies that there are two diodes. There is a resistance, inductance, and back EMF. This is same. You have an inductor, you have a resistance, you have a back EMF. So till now everything is same. This is, let's say, D1. Now you have additional diode connected here, which is D2, right? And this additional diode is called as freewheeling diode. I'll tell you why we are calling it a freewheeling diode. So let us start drawing the waveform. Let us start with voltage source, which is V in. Right, this is V in waveform, wherein you can also draw E. This is E, right? And this is the angle alpha. Now let us again start with the assumption that initially the inductor current is 0. So this is your I here, right? Here there are two different currents. One is the input current I in, right? And another one is the current I, which is the inductor current. So let us go by the initial condition. Let us assume that initial condition is 0. If that is the case, then you can see that initially current is 0, right? Your voltage E is more than V in, and therefore the diode D1 would remain reverse bias. Moreover, E would try to force a current, but then it cannot flow through D2. So therefore D2 would also remain reverse bias. So both diodes would be reverse bias till the point alpha. At point T plus, at instant alpha plus, just after the instant alpha, you would see that the input voltage would become more than E, and that would help us increase the the inductor current to rise slowly, right? So after alpha, the inductor current would rise, and again it would hit a peak value at some instant, right? And after that instant, the current would fall, and current would continue to fall till pi, right? Now if you see, I is positive, there is a current is flowing in this direction, current is positive, right? And you have reached the instant pi. Now this is a common cathode configuration, right? So which diode would conduct? Which has higher anode potential. So at pi minus, just before the instant pi, V in is positive, and therefore anode of diode 1 is greater than anode of diode 2, and therefore diode 1 was conducting. So in this duration, D1 conducts, right? But as soon as you cross pi, then V in becomes negative, and therefore D2 will start conducting instead of D1. So after this instant, D2 will conduct. And now if you see the KVL equation, how does it change? For instance, for duration between alpha to pi, the equation was V in minus LdIL by dt minus, you can say, just current I LdI by dt minus Ri minus E is equal to 0, right? And therefore the slope was written as V in minus Ri minus E is equal to L di by dt, right? So the current was falling with a certain slope. Now suddenly at theta greater than pi, you see V in will go away and you will have 0 minus Ri minus E is equal to L di by dt, right? Now at just before this, the V in value was just before. Now ideally what would have happened is that if this diode would not have been there, this V in would have become negative, right? And it would have continued to fall the current at a faster slope, because this is negative, this third term is negative, so the slope would have fallen very steep. But now because this term has become 0, only there are these two negative terms, the speed at which the current would fall would reduce. And let's say in the previous circuit where the freewheeling diode was not there, if the current would have come to 0 at this instant, here the current might continue and come to 0 at a later instant, right? So the current path will become this. Now this second part is almost again it's not a straight line, it is a solution to this equation number 2, right? But I've approximately shown it as a straight line, but this is actually a solution of equation 2. So this is how the current would look like in this case. Now let us see, have we solved our first problem? The first problem was in the previous circuit that the power, instantaneous power coming from the input should not become negative, right? Here I have drawn I, you can also draw what is I in. So I in is nothing but up to this instant. Why? Because after this diode 1 stops conducting, so it becomes 0. So here if you see, the instantaneous power is always greater or equal to 0, but it never goes negative, and therefore you are never pushing back power into the source. So that was our first limitation. The second limitation was in terms of the voltage V1. How is the voltage V1 look like? So the voltage V1, let me draw it here, would look like, it will be initially be E, then it will be like this, and then it will follow till this point. Then it will not go negative because D2 starts conducting, it will remain 0 till the instant when the voltage again becomes equal to E, right? So again in V1 the negative part is not visible anymore, and therefore you can assume that the ripple would reduce slightly. I mean, ideally you would want V1 to be constant, but that may not happen. But certainly the performance of this circuit in terms of ripple would be better than the previous circuit. So because the voltage ripple is less, therefore the current ripple is also going to be less. If the current ripple is less, the DC motor would have a current which is more close to a DC current, right? So the current ripple is small, and because of that the torque ripple would also become small, because torque is proportional to the armature winding current, right, in a DC machine. So therefore this helps us reduce the current ripple and takes care of both the problems, right? And D2 is called as freewheeling because it just freewheels, right? It freewheels while V1 remains equal to 0. When D1 conducts, V1 becomes equal to V in, and when D2 conducts, V1 remains 0. So this is how the circuit actually operates. Now if you see, what happens is, now here the chances of the circuit going, even though the particular waveforms that I have drawn was actually for a discontinuous conduction mode, but you see after this point pi, right, there is, if depending on the value of E, let's assume that E is small. If E is small, it may so happen that the slope might be lesser, and if the slope is lesser, then we may not really end at 0, we may end at a positive value, and therefore next cycle again it will start at a positive value, right? And because next cycle will start at a positive value, that means that as soon as the if the current is there, if the current is positive, right, and starts at the positive value, in that case you can see that one of the D1 or D2 has to conduct. So even in the first period also you would see that D1 will conduct, and if D1 will conduct, this current will fall, and then it will again rise, and then it will fall, right? So you see that there is a possibility of the circuit operating in continuous conduction mode also, right? Unlike the previous circuit, which was expected to operate in discontinuous conduction mode, this circuit here can operate in continuous conduction mode also. So this is also one of the feature of this freewheeling half wave circuit. Okay, now let's say if somebody asks you to calculate certain average values, right? Yes, there is a ripple and you might be asked to calculate some ripple values, but at the same time you might be asked to calculate just the average values. If you see, average value calculation can be done in this way. So let me write the KVL equation starting from V1, inductor, resistance, and E, which I have already in a way written. So in general you can write V1 is equal to E plus L di by dt plus IR, right? Where what is V1? V1 is the voltage across the load. This is an instantaneous value, right? So all of these parameters, E is a constant, but current is a function of time, right? And V1 is also a function of time. Now I can always integrate this equation with respect to dt over the complete period capital T, and I can do that on both sides, right? Time going from 0 to capital T, time going from 0 to capital T plus L right, and all of them would have 1 by T. Now the next step is, what is this left thing? This is nothing but the average value of voltage V1, right? What is this second term? This second term is nothing but average value of E. Now if you assume E is constant, it is nothing but just E. What is the third term? Third term is, if you see, it is the average value of the inductor voltage. Why? Because inductor voltage is L di by dt. So this is VL dt integral 0 to t. This is average voltage across inductor, right? And as we have seen that in steady state, the average voltage across inductor is 0. So if you consider your circuit operating in steady state, what is steady state? If you see this waveform, you understand in the first cycle the current may not necessarily current is not starting from 0 and may not end at 0, may end at a positive value. Second cycle will start a little bit positive, end at a further positive value, and so on. But after multiple number of such cycles, the current would achieve a steady state wherein the starting point of the current would match the ending point of the current, and that is the point we call it as steady state. And therefore at steady state, the average voltage inductor across inductor has to be 0. What is the third term? Third term is again R into average value of current IO, or just I. So if you see, this thing becomes really simpler to solve. For example, if you have been told about the instant alpha, and if you understand that this would operate in continuous conduction mode, then you can just solve for average value of V. You know average value of E, you know R. You can solve for average value of current. You can do that. You can apply this thing in both CCM and DCM. The only thing is that in CCM, finding the average value of V is much simpler, because you know how the voltage waveform is. But in DCM, it is a function of the angle gamma. In CCM, you know what is beta for diode D1. Beta for D1 is nothing but equal to pi. So at pi, the diode stops conducting, right? If you are operating in discontinuous conduction mode, then what happens is, if you see the waveform, there is going to be E, right, starting from this instant when the current becomes equal to 0 till this point, and therefore this instant becomes important while calculating the average value of V1. And therefore in DCM it may be a little bit more challenging. In CCM it can help you solve the problem really fast, right? So if the question says that you consider sufficiently large value of inductor, right, that's usually a language used, sufficiently large value of inductor, that implies is that inductance is large in this circuit, right? And we understand that this circuit has the capability of going into CCM. So therefore it makes sense to use to assume that the circuit is operating in CCM for a large value of inductor. And then you can apply the average equation. Average equation becomes average of V1 minus E upon R is nothing but average of current in this case. Okay, so far so good. I think we have talked about this half-wave freewheeling circuits. Now, if you see any, you can also let me just you can also do one more thing. Let's say any half-wave circuit, right? Any half-wave circuit. You can take the one with freewheeling diode, but you can have a look at other circuits also. If you see the one with freewheeling diode, as we have seen, how would the input current look like? So initially the input current, let's say, falls, then it rises, right? And then again it starts falling at some instant, and this is where you hit pi. And then after that it remains 0 till 2 pi, right? This is roughly the input current waveforms look like, right? Maybe I've not drawn it properly, something like that maybe, right? This is how the input current waveform look like. What is input current? Let me quickly show you guys. Yeah, this is the input current which is coming from the input source. So essentially the thing that you draw as a AC source, it's giving you this kind of current. If you do Fourier series expansion of that, right, if you do a Fourier series expansion on that, what you see is that you have a DC component plus you also have 50 Hertz component, right, assuming your power cycle is 50 Hertz, and you may also have higher frequency components, right? So other frequencies are still okay, but you have to notice that there is a DC component, right? What does it mean? That if you find the average of the input current, it is not going to be equal to 0. So the input current is going to have a DC component. Now this DC component drawn from the input AC source is not very good thing. Why is that? Let's see. Let's consider a scenario where you have a grid, right? Now what is a grid? A grid is nothing but it steps up, steps down, right? So there are so many transformers in connected in this system. So let's say you get an AC source at your home. Now obviously it is coming through some kind of step down circuit, a distribution transformer. So let me draw that step down circuit here. This is the distribution transformer, right? Let me also draw the magnetizing inductance of this transformer, right? And let's say this line has some series resistance and some inductance. These are the line inductances, or these could be the leakage inductances of the transformer also, right? So this is a transformer. And now here, let's say this point comes to your home, right? And wherein you have connected this series diode based circuit, right? Something like this. Or for that matter, any half wave circuit. Let's say this is how you have connected this circuit. Now we have seen that this input current has DC component in addition to AC, right? Now where will this DC current flow from? Now DC current can flow, if you see this is a transformer, right? The full thing is a transformer. So this part is nothing but an ideal transformer, right? And therefore the DC current, only the DC component which is flowing in this path, for inductor would act as a short circuit for DC, so it can actually flow from here, right? Most majority of the DC, it might flow, it can think of flowing from here and then flowing from here because it's an ideal transformer, but then this there would be a series impedance, and therefore this might be a lower impedance path for the current to flow through. So what happens is your magnetizing current of the distribution transformer is not only AC, it is AC definitely, plus it also has a DC component. If you draw the BH loop, B is the flux density. So that means you do have if this is your BH loop, this is your BH loop, right? So that means you have a DC component. That means DC component is, let's say, contributing to this much of flux. This is BDC, right? And you would have an AC. So you would be actually going above and below this point. So because of this DC offset, what has happened is you are tending more close towards saturation. If you did not have this AC current, then what will happen? Then you would be actually pretty far from the saturation, because you will be at the middle and you would be oscillating in this direction. Let's say, let me draw it here. So if you do not have DC current, then you would have something like this, right? Equal on both sides. Now what has happened is, because this midpoint has shifted up, your bottom point has shifted up and your top point has further gone into saturation. So the chances of your substation transformer getting saturated is increasing, right? Which is not desirable, which is not good, because the transformer was not designed for saturation. If it is moving towards saturation, you can understand that it would start drawing large amount of current from the grid, large amount of current, non-linear current from the grid, because it goes into saturation, which is not desirable. And therefore, in general, the half wave rectifiers are not a good solution as a rectifier circuits. And to be very honest, they are rarely used in practical circuits. They are used, but for very very low power, so much low power that it does not really impact the substation transformer. But as you increase the power, then because you are increasing power, your DC component of the current will also increase in such circuit, and which might saturate your transformer. And therefore these circuits are not generally recommended for slightly more power, right? They are used for very very low power, if at all you probably end to use it, right? This is one of the limitation which exists with the with the half wave circuits, or we call it single pulse circuits, right? So let me just write it here. Half wave DC input current implies transformer saturation, implies not used for more power, used for very very small power, right? So this is one of the major limitation of such half wave rectifier circuits. And therefore now in the next video we would talk about full wave diode bridge rectifier circuits.